Let us begin with the module on lasers. Laser is very effective power source and it has number of applications like in biomedical field or in military applications, in laboratories, in research laboratories, etc. It is mainly used in number of optical sensors. Laser is acronym of light amplification by stimulated emission of light. Laser is a power source we say, but it is actually sending a light of a particular wavelength. There are other light sources called as the conventional light sources which are available, but number of advantages are observed for lasers as compared to these conventional light sources. So, in this module we will first see what are the properties of the laser and how they are advantageous over the other conventional light sources. In the first part, we will understand the different properties of laser, like first we understand what is coherence, then what is directionality and monochromaticity, and overview of laser intensity range and short pulse generation. In the next part of the same module, we will describe some pumping schemes, some drawbacks of two laser pumping scheme, what is 3-level laser system, understanding the working of ruby laser, and finally we summarize the module. So, let us begin with the concept of coherence. Laser light differs from conventional light in number of ways. Laser have high degree of coherence which results into highly monochromatic and directional beam of light. Lasers are available with output powers from milliwatt to kilowatt. Lasers are available in both continuous and pulsed operations. In pulse mode, laser pulses of the order of nanosecond, picosecond and femtosecond can be produced using some techniques like Q switching and mode locking. Such unique properties can be explained in various applications. Now, let us begin with the properties of lasers, and the first one is the coherence. Two light waves are said to be coherent if they follow a definite phase relationship with each other. Figure in the slide shows what do you mean by coherence. Here you can see that there are two waves which are exactly in phase, that is their crests and troughs, they are exactly matching. However, if we are considering the next figure, here the two waves are coming at different time, hence they are not having the same phase or they are incoherent. Coherence requires that there is a connection between the amplitude and the phase of the light at one point and time and amplitude and phase of light at the another point and time. Accordingly, coherence is of two types: spatial coherence and temporal coherence. Let us see what is spatial coherence. Let us consider 2 points P1 and P2. At time t is equal to 0, they lie on the same wavefront of the given electromagnetic wave. Let E1t and E2t are the electric fields at these 2 points respectively. The phase difference between the fields will be 0 at time t is equal to 0. If the difference remains 0 for any time t greater than 0, there is a perfect spatial coherence between 2 points. If this is followed by every point on the wavefront, then the wave has perfect spatial coherence. In practice, if the points lie within some area around P1 has good phase correlation, then the wave has partial spatial coherence. So, in partial spatial coherence, for any point P, there will be suitably defined area SCP called as the coherence area. Lasers have high degree of spatial coherence as compared to conventional light sources. Consider the electric field of the electromagnetic wave at a given point P at time t and t plus tau. If for a given time delay tau, phase difference remains constant, we say there is a temporal coherence over the time tau. If this occurs for any value of tau, then wave is having perfect temporal coherence. And if this occurs a time delay which is in between 0 to tau 0, then wave is having partial temporal coherence with the coherent time tau 0. The figure shows that wave has a phase jump after time interval tau 0. Now, let us go for the next property, that is directionality. Conventional sources of light are highly divergent sources, and light from these sources spread in all directions. When for certain application a narrow beam of light is required, an aperture is kept in front of the source. This reduces the intensity of the light. Lasers are highly directional in nature. Up to certain distance, beam shows little divergence and remains essentially a bundle of parallel rays. The directionality is measured in terms of divergence angle of the beam. It is called as full angle beam divergence, which is twice the angle that the outer edge makes with the axis of the beam. The outer edge of the beam is the point at which the intensity of the beam has dropped to 1 upon E times its value at the center. When a beam with plane wavefronts radiates from an aperture of diameter d, beam propagates as parallel beam for a distance of about d square upon lambda, which is called as the Rayleigh range, and then spread with distance due to diffraction effects. The full angle divergence is given by the formula 2 theta is equal to 4 lambda upon 2 W0 pi, where 2 W0 is the diameter of the beam waist. For laser, typical value of divergence is about 10 raised to minus 3 radian. It means for every 1 meter, the beam spread is less than 1 millimeter. Directionality is the direct consequence of placing active medium in between two parallel mirrors. Due to mirror arrangement, photons travelling along the axis or little bit deviated will be able to bounce back in the cavity. Photons moving away from the axis of resonator will be rejected by the cavity. As shown in the figure, ray 1 is travelling along the axis, so will be sustained in the cavity. Ray 2 will not be reflected from the mirror, so rejected by the cavity. And ray 3 having little deviation from the axis but will be sustained in the cavity due to multiple reflections through mirrors. In lasers, output of laser is many million times focused than the best searchlight that is available. Hence, lasers can be used to monitor distant objects. For example, Earth-Moon distance is monitored using laser. For this, retroreflectors are mounted on the moon during Apollo programs. The total time for the beam to do to and fro journey is measured, and it is found that the moon is moving away from the earth every year by few inches. Let us see some different types of light sources and their wavelengths in nanometer. So, you can see the spread of wavelength, that is delta lambda, for these sources. For example, if you consider the noon sunlight, then the wavelength range is 400 to 700 nanometers. For tungsten lamp, it is 400 to 700 nanometers. White LED also the same range, and for the mercury lamp also the same range is emitted. Barcode scanning laser, if we consider, then you can see that delta lambda is very small, that is 630 to 680 nanometers. Let us see the range of available powers of lasers along with the applications in which these type of lasers are used. If we consider the laser having the power of 1 to 5 milliwatt, then it is used for laser pointers. If the power is 5 milliwatt, then it is used in CD-ROM drives. 5 to 10 milliwatt used for DVD players. 100 milliwatt is used for high speed CD read and write burner. 1 watt is used for holographic disc. 30 to 100 watt used for surgical lasers. 100 to 3000 watt used for cutting, drilling and welding. As we have seen different properties of lasers like directionality, monochromaticity, coherence. In addition to this, we should know how pulse is generated from the laser. In the previous module, we have seen that how stimulated emission is used for the emission of light from laser. Here, population inversion is the basic principle. The population inversion is achieved by using the pumping mechanism. There are number of pumping mechanisms, like we can have a 2-level system or a 3-level system. There are certain drawbacks which are associated with 2-level system, because in 2-level system population inversion is not achieved easily. This is because the electrons will remain in the higher energy state depending upon its lifetime. So, in this particular laser, the pulse is generated because of the population inversion, and there is a pumping mechanism which will do this population inversion. Number of photons which are incident on the particular material, it will generate large number of photons, again they are multiplied, and through the semi-transparent mirror these photons are emitted out. So, suddenly large number of photons are emitted out and hence a pulse is generated. In the diagram, you can see a 2-level pumping scheme. In 2-level pumping scheme, it is difficult to attain the population inversion. This is because of 2 reasons. Firstly, if excited level is to be a metastable level for population inversion, then it will be less prudent and hence a narrow bandwidth is there. The pump will be required to pump atoms from ground to excited level. Secondly, the same pump which is used to excite the atom can also cause de-excitation of atoms to ground level. Due to this, suitable pumping schemes to generate laser light are 3 and 4 level pumping schemes. Three-level pumping scheme. A model of a 3-level pumping scheme is shown in the figure. 3 levels of the atom are used to get the laser in this scheme. The first level is ground level EG, from where atoms are transferred to the level EP called as the pump level. EP should be a band of energy levels and a short-lived state. Atoms decay by non-radiative way to level EL as soon as they excited to EP level. EL level is a metastable level, So, atoms stay in this state for longer time and large number of atoms will be accumulated at this level. Transition from EL to EG is radiative and gives laser light of frequency mu is equal to EL minus EG upon H. Most of the lasers using this type of pulse scheme are pulse lasers, and the example is ruby laser. The ruby laser is the first working laser made by Theodore Memon at UJ's research laboratories in 1960. Ruby laser produce visible light at wavelength of 694.3 nanometer, which is a deep red color. Its output is in the pulse form of pulse lengths of the order of a millisecond. Now, let us see what is the active medium in the ruby laser. Active medium is a ruby crystal which is Al2O3 doped with chromium ion at a concentration of 0.05%. These chromium ions constitute the active centers. These centers provide a set of 3 energy levels suitable for lasing action. You can refer to the figure shown on the slide. Level G is ground level and E1 and E2 are the pump bands. M is the metastable level, which consists of 2 closely spaced levels having lifetime 3 milliseconds. Lasing transition occurs between M and G level gives rise to light of wavelength 694.3 nanometers. So, let us see which pumping source is used for this purpose. Ruby laser uses optical pumping source. Light emitted by xenon flash lamp is absorbed by chromium ion at ground level G. Ruby has very broad and powerful absorption bands in the visual spectrum at 400 and 550 nanometer and a very long fluorescence lifetime of 3 milliseconds. After absorption, chromium ion jumps to excited band either E1 and E2 depending upon the wavelength of absorption. This allows for very high energy pumping. In the figure, flash lamp is used in the helical form. Another design that is used for pumping by xenon flash lamp is linear lamp design, which most commonly used now. In this design, laser rod is kept in an elliptical cavity with a linear flash lamp at the focus of internally reflecting cavity. This assures the efficient pumping of ruby crystal. The mirrors are placed outside. Xenon flash lamp lasts for few milliseconds. However, laser does not operate in this time, so output of ruby laser is pulsating. Figure shows the output of flash lamp and spikes in the output of ruby laser. Now, let us see the properties and applications of ruby laser. In ruby laser, the active medium is ruby crystal. Pumping is done by optical pumping by using xenon flash lamp. Wavelength is 694.3 nanometers. Power output pulse energy of 100 joules and pulse duration is in milliseconds. The efficiency is 0.121%. And different applications are for range finding, for drilling holes through diamond and also in holography. Let us see 4-level laser system. In 3-level pumping scheme, 3 levels of atoms are used to produce laser, but in most of the cases this scheme gives a laser light in the form of pulses. In 3 level laser system, population of excited level is compared with respect to ground level, and hence it requires high pump power to achieve population inversion in lasing medium that causes low efficiency of laser. A 4 level pumping scheme uses 4 levels of atom to produce the laser. Figure below shows typical 4 level pumping scheme. In this scheme, pump transfers atoms from ground level to level EP. EP is a short-lived state, hence atoms drop to a level EULL by non-radiative transition. EULL is upper lasing level and is a metastable level. Atoms stay here for longer time and population inversion is achieved. From level EULL, atoms do a radiative transition to ELLL state and emit photons of frequency mu is equal to EULL minus ELLL upon H. ELLL is a low lasing level and population of EULL level is compared now with respect to ELLL level. From ELLL atoms de-excite to ground level by fast non-radiative process and available for next cycle of lasing. As the terminal level ELLL is virtually vacant, population inversion between EULL and ELLL achieved quickly. In contrast to a 3 level pumping scheme, lower lasing level is not ground level, so as soon as any atoms comes to upper lasing level EULL, population inversion is established. Thus, it requires less pumping energy than 3 level pumping scheme. So, let us see one example of the most popular 4 level solid state laser is ND-YAG laser. The laser operation of ND-YAG was first demonstrated by J. E. Gouchiet al. at Bell Laboratories in 1964. In this, the active medium which is used is the ND-YAG, that is neodymium doped yttrium aluminum garnet, that is NDY3Al5O12 is a crystal that is used as a lasing medium for this laser. Since the two ions are of similar size, triply ionized neodymium replaces small fraction, that is 1% of the yttrium ions in the host crystal structure of the yttrium aluminum garnet, that is YAG. It is the neodymium ion which provides the lasing activity in the medium in the same fashion as chromium ion in ruby lasers. Let us see the energy level diagram of ND-YAG laser. The lower lasing level E2 is sufficiently far away from the ground level. The two primary pump bands E4 are in 0.73 micrometer and 0.85 micrometer range. In transition from E4 to E3, energy is released to crystal. E3 is a metastable state. As E2 is located at 0.25 electron volt above the ground level, it cannot be populated by thermal transitions from ground level. The population inversion between E3 and E2 can be readily achieved. From E3 to E2, Nd3 plus ions are stimulated to emit on the wavelength of 1.064 micrometer laser transition. From E2 to ground, Nd ions drop to ground level by fast non-radiative transition. Pumping source. Optical pumping is used for Nd-YAG laser. Xenon flash lamp is used for pulsed operation and tungsten halide incandescent lamp for continuous wave, that is CW operation. A gallium arsenide diode laser also used for pumping. A typical design of Nd-YAG laser is shown in the figure. It represents an elliptical design of the cavity in which lamp and Nd-YAG rod are kept on two focus of the cavity. Following table gives the properties and applications of Nd-YAG laser. In this, the active medium is Nd3 plus doped in YAG. Pumping mechanism used is optical pumping, that is xenon flash lamp for pulsed output and tungsten halide incandescent lamp for continuous wave output. The wavelength that is achieved is 1064 nanometer or 532 nanometer in second harmonic generation. Power that is generated is having the pulse energy of 1 kilowatt for continuous wave. Pulse duration Q switched Nd-YAG laser, efficiency 3%, and applications are in medicine, welding, cutting, drilling, military and defense, and spectroscopy. Let us see next type of laser, that is tunable lasers. A tunable laser is a laser whose wavelength can be controlled over a range. Only a few types of lasers allow continuous tuning over a significant wavelength range. There are various types and categories of tunable lasers. They exist in gas, liquid and solid state. The examples of tunable lasers are excimer laser, CO2 laser, dye laser, semiconductor lasers, etc. Tunable lasers find their applications specially in spectroscopy, photochemistry, laser isotope separation and optical communications. No real laser is truly monochromatic. All lasers can emit light over some range of frequencies known as the line width of the laser. In most lasers, with line width is quite narrow, hence they are treated as nearly monochromatic. Within the line width, if the output of the laser can be tuned, it is called as tunable laser. An example of tunable laser is discussed in this particular module. Let us consider the first one as dye laser. In dye laser, it uses organic dyes as lasing medium. It is used for large range of wavelengths, and this type of bandwidth is particularly made usable for tunable and pulse laser. This laser consists of organic dye mixed with solvent, which may be circulated through a dye cell. Some of the laser dyes are rhodamine, fluorescein, coumarin, stibine, umbelliferone, tetrazine, melachin green, etc. A variety of solvents can be used such as water, glycol, ethanol, methanol, hexane, cyclohexane, cyclodextrin and others. Let us see some applications of lasers. As we know that laser is a coherent light and it has high monochromaticity, it has wide range of applications in physics, chemistry, medicine and technology. If we consider in physics, then it is used in atomic and molecular spectroscopy, interferometry and holography, and cooling of atoms. If we consider how it is useful in chemistry, then element trace detection, photochemistry and photopolymerization effect. is studied by using these lasers. In medicine, ophthalmology, dermatology and cosmetics, nanotechnology, biosimulation, surgery, etc. are the fields in which these lasers are useful. And if we consider the technology, then it is used in material processing, time and length standards, metrology, entertainment, electronics, tele and optocommunications. Let us see these applications briefly one by one. Now, let us see this how the laser can be used for material processing. Ultra fast laser pulses with proper energy density and wavelength are now used for processing materials where thermal influence must be minimized, including drilling of metals and cutting of wafers. Lasers are highly intense and can be focused to a spot size of micrometer. Due to this high focusability and small time scale, lasers are used for cutting, drilling and welding of all types of materials, namely metals, non-metals, plastic and wood, etc. A laser with wavelength lambda and spot size A can be focused with a lens of focal length up to spot size B, which is given by B is equal to lambda f upon A. If we consider the ND-YAG laser, the parameters are lambda is equal to 1.06 micrometer, A is equal to 1 centimeter, F is equal to 2 centimeter and P is 1 watt. Intensity of the laser at the focal spot is I is equal to 7 into 10 raised to 6 watt per meter square. Now, let us see how the lasers are used in medicine. Lasers are used in medicine, they are of different types. They are used in medical diagnosis, treatment or therapy. Types of lasers used in medicine include in principle any laser design, but specially CO2 lasers, diode lasers, dye lasers, excimer lasers, fiber lasers, gas lasers, free electron lasers, optical parametric oscillators and medical areas that employ lasers. They include angioplasty, cancer diagnosis, cancer treatment, cosmetic applications such as laser hair removal, tattoo removal and laser liposuction dermatology. Then lithotripsy, mammography, medical imaging, microscopy, ophthalmology that include LASIK and laser photocoagulation, optical coherence tomography, prostatectomy, surgery. Laser energy can be concentrated into small area which gives possibility of cutting and vaporizing the tissues. It is due to these qualities that the laser has become so important in laser surgery. Its advantage being the possibility of performing a non-contact sharp contour tissue incision and removal of even tiny structures without any damage to the surrounding tissue and any possible infection of the cut. Laser surgery thus makes use of transformation of radiation into heat within the tissue, thus performing both an incision and coagulation. Monochromaticity and coherence, two properties of laser radiations, are utilized mainly in medical diagnosis. Holography with lasers. Holography is a technique which enables three-dimensional imaging of objects. The image changes as the position and orientation of the viewing system changes in exactly the same way as if the object were still present, thus making the image appear three-dimensional. A hologram is an interference pattern of an object, hence coherent sources of light like lasers can be used to make hologram. Holograms are recorded using a flash of light that illuminates a scene and then recorded on the recording medium. In addition, however, part of the light beam must be made incident on the recording medium. This second light beam is known as the reference beam. A hologram requires a laser as the sole light source. Lasers can be precisely controlled and have a fixed wavelength, unlike sunlight or light from conventional sources which contain many different wavelengths. In hologram, both amplitude and phase of light reflected from object is recorded. A hologram represents a recording of information regarding the light that come from original scene as scattered in the range of directions rather than from only one direction as in a photograph. This allows the scene to be viewed from a range of different angles as if it will be present there. A holographic recording requires a second light beam, the reference beam, to be directed onto the recording medium. A photograph can then be viewed in a wide range of lighting conditions, whereas holograms can only be viewed with very specific forms of illumination. When a photograph is cut in half, each piece shows half of the scene. When a hologram is cut in half, the whole scene can still be seen in each piece. Laser fusion. Energy created by hydrogen fusion reaction within the sun. Nuclear fusion is the process in which two atoms fuse to make bigger atom, and huge amount of energy is released in the process due to mass defect. If fusion could be created artificially, then people could solve two of the Earth's largest problems of energy shortage, and that could save the environment. That is possible when practical laser fusion technology could be realized. Let us conclude with the module. Laser is the acronym of light amplification by simulated emission of light. Here, the light is amplified by different pumping mechanisms. But before that, how laser is more beneficial and advantageous over other conventional light sources is explained in this particular module. The main properties which are associated with lasers are high monochromaticity, directionality, and coherence. Due to this, it is the most effective, useful power source which is used in number of applications like in military, in biomedical, in industries also. So, here we consider first the pumping mechanisms which are associated with the laser. The amplification and population inversion are the two basic things which are required for the stimulated emission. The pumping is achieved either by a high optical source or by some electric field or some other means. In this particular module, two basic pumping mechanisms are described. They are two-level system, three-level system. The limitations of two-level system are described in detail, and how three-level system is always necessary for getting the lasing action, that is also described in this module. Ruby laser is one of the example of three-level system. So, let us conclude with this module. Thank you very much.